to Monday night. So this weekend might be the best time to get down there. Hopefully those who've gone to it already didn't have much in the way of problems, and the questions made sense and so forth. So, all right. So, class is too big, and it would be nice to do an organized trip down there, but it's kind of hard to do an organized trip that could all be on the same time. So, last time we were looking at dinosaur eggs and babies, and looking at dinosaur growth. We got to the question, let's back up here, how long did it take to grow all from a little baby, up to an adult? And as I mentioned, for the 19th and 20th century, we didn't really have metrics by which to judge that. But at the dawn of this century, new work, which actually technically was based on work that he was doing in the 1990s, Greg Erickson and colleagues developed the use of these growth rings that occur naturally in lots of vertebrates as an estimate of figuring out how old the dinosaur or other organism was at the time of death. And just to remind you of this practice of this technique of skeletochronology, so aging based on the skeleton, there's an attribute of vertebrates that they typically, not all groups, but typically lay down a observable growth ring once a year. And it represents having a phase of more rapid growth during the year and then a slow down phase. And so if you have a section of bone, you could slice it up and count the rings, and then you know the age. Now, that's a simplistic way of looking at it. You have to accommodate the fact that bone is a living tissue, that it modifies, that parts of it get resorbed. We'll talk more about that next week. And so some allowances have to be made. Not all bones mark the growth rings equally well. You want to sample multiple bones for every individual. But in broad strokes, you cut open a bone, you count the growth rings, and it tells you how old the animal was at the time of death. So these markers are called lines of arrested growth, or lags. There's a couple other terms used for them, but lag is sort of the traditional one. That's what we'll go with. So this particular bone in the Tyrannosaur and Gorgosaurus shows 5 growth rings, 5 lags, and so it was between 5 and 6 years old at the time of death. Or over here, this is the rib of the specimen of Tyrannosaurus called Sue. So one of the largest specimens. It's on display in Chicago, and it shows in this section's rib, it's got 19 clear lags, but then at the outer rim of bone, there's actually a whole bunch of lags there stacked on top of each other. And what that means is that the animal was still alive, it was growing, but it has essentially achieved full body size, so it wasn't growing very much. And this represents what's called the external fundamental system, or EFS. When you find an EFS on a bone, it tells you the animal has achieved full body size, and that if you can manage to count the growth rings within the EFS, you can add those to the other growth rings and figure out how old the individual was at time of death. In this case, it shows that the specimen called Sue died around the 28th year of life. Now, that was when this figure was made. Actually, there's been some recalibration of these earlier growth rings. It may be closer to 33, but at least they got in the same ballpark to begin with. And so, that gives you the age of an individual at time of death. But if you have multiple individuals of the same species, and those individuals were of different ages at time of death, they can help create a better picture of the growth patterns of that species. So for instance, here are 3 individuals of Tyrannosaurus, and I just want to say, none of the skeletons anywhere near complete. In fact, this skeleton isn't a skeleton. It's some bits of bone from the skull. That's about it. And I have quibbles with the way they restored the body, but hey, that's just professional comment. So by taking individuals of the same species at different ages, different body sizes, you could create sort of hypothetical growth curves for an individual species. In this case, we see genera, but each of these is known from only a single species, so that works out fine. So, for one individual, you get a mass estimate at the time of death, and you can get an age at time of death and a mass estimate at time of death. And plot these up for one species, it gives you a growth curve. And so here we see for Tyrannosaurus that they start off, it looks like 0, but consider the scale here. These are tons. Well, 6 tons, 5 tons, 4 tons, etc. So, that's smaller than a human. It looks like 0 at this time scale, or this mass scale. And so we see what looks like a period of relatively low growth, then a phase of rapid growth starting about age 11 or 12. That phase of rapid growth peters out in the late teens, and then the oldest individuals in their late 20s or now possibly early 30s. Now, in some ways, that growth curve should sound familiar. Relatively low growth rates until about age 12, rapid growth rates between about 12 and 18, and slowed down after that. That's a human growth curve, if you don't mind the masses there. It's just coincidence that T-Rex happens to have a human-like growth curve, at least for the phase up to achieving full body size. But a pattern that has been consistently seen across Dinosauria is that we don't tend to find individuals that lasted a long time after achieving full body size. And this is in marked contrast to looking at placental mammals, both large placental mammals, both extant and extinct. The earlier part of the growth curve might be similar in many ways to modern placental mammals, so achieving full body size, in the first couple decades of life. But big mammals like rhinos and elephants and so forth today tend to persist for a longer period after they achieve full body size than they had before achieving full body size. Dinosaurs, very different. So this is from one of the initial studies from 2001. And we've got dinosaurs ranging from tiny little Shibuya, which is a small alvarosaurid, up to Apatosaurus. And this is a more recent paper looking at a variety of sauropodomorphs. And you'll see that most of these animals, most of these dinosaurs are achieving full body size before they're 10. In the case of Apatosaurus, maybe a little after that. Same for Massospondylus. These are more updated versions, and we see Apatosaurus is achieving full body size maybe in its late or mid-20s or so. But some individuals, again, mid-20s or so. But none of them seem to persist terribly long after they achieve full body size. Now, that's in marked contrast with other giant sauropsids, other giant reptiles. For instance, there were giant crocodilians that lived in the same environments at the same time as dinosaurs, like Deinosuchus here, a giant alligator relative. And we can look at its growth curve and find that, now this is length rather than mass, but it is continuously growing throughout its entire life history, which is a similar pattern to what we see in modern crocodilians. So the green is alligator, or whatever color we want to call that. The yellow is the saltwater crocodile. And we do notice that, this giant Cretaceous crocodile is growing faster than modern crocs, but not tremendously faster. And in fact, that's something else people were able to take a look at once they established these growth curves, is that you could look, and there's a bunch of different ways you can do this, and people argue over what is mathematically and statistically the soundest way of doing it, but the net results are typically the same. If you find the phase of most rapid growth, you could plot that up for both modern and extinct animals, and we find that non-avian dinosaurs, dinosaurs other than birds, are the ones in the squares, and they're forming this line here, which is plotting among the eutherians, those are placental mammals, precocial birds, so again, birds who are able to walk around at hatching, like chickens and ostriches and so forth, and marsupial mammals. They plot higher than cold-blooded modern reptiles, and higher than fish, but lower than altricial birds, which have the fastest growth rate of any vertebrate today. So remember, altricial birds, birds which are nest-bound, which are helpless at birth. And notice that these are log scales here. So, this is 10 times that, that's 10 times that, or 100 times that, and the same as the log scale down here as well. So, dinosaurs are showing growth curves comparable to ground birds, ground-dwelling birds, and marsupials and placental mammals, and that will be an issue that will come up next week as well. So we see that dinosaurs grew quickly, much faster than similar-sized crocodilians in the same environment. So we can't say, or is unlikely to say, that the high growth rates of dinosaurs were due to the Cretaceous being a warmer and more favorable climate to reptiles. I mean, this difference here, that's probably attributable to that, but not from that to that. So, again, dinosaurian lifespans, as I mentioned, we once considered the possibilities. They might have lived for centuries, literally. Modern giant tortoises can live for centuries, barring accident or disease. There was a tortoise that recently died that was collected by Charles Darwin in the Galapagos. There was an adult Aldabran tortoise that died after 180, I believe it was, years of continuous captivity by Dutch troops in Indonesia. It was fully grown when acquired and was accounted for almost 200 years. So. But it turns out that's not the case with dinosaurs. Small ones seem to have lived less than a decade. Medium-sized ones or large ones, just a couple of decades. The oldest T-Rex was on the order of about 30 years. The biggest sauropods we have seem to be in the 50 to 60 age range or something like that. Not the 90 or 100 range that a big elephant might be able to do. Certainly not the whale. Possibility some whales can live for centuries. So, just recently, actually, within the last 20 years, a whale was found, and it had died just recently. It had a harpoon in it from the days of harpooning, by hand. This wasn't like a 20th century gas-powered harpoon. This was like a Moby Dick era harpoon in it. And so this is a weird pattern compared to modern birds and modern placental mammals. So this is scaled not to years, but to percent of the whole lifespan. Modern birds and modern placental mammals, the big placental mammals, achieve full body size quickly and then persist for long periods of time. Whereas dinosaurs, which are, well, the green one here is a crocodilian, alligator in fact, all the other ones are dinosaurs. Non-avian dinosaurs seem to have had just a small fraction of their life at full body size. And that, like many modern animals, there's a high rate of mortality when they're very young, but, a not super high rate of mortality for a wild animal in later parts of the year. Also to throw in here, as you see on this age along the bottom, and it's like, we see that as time goes by, getting bigger and bigger animals, sexual maturity shows up in dinosaurs based on things like the presence of medullary bone and so forth. Fairly early. They're not fully grown. And at first people would say, that's weird. That's true of us too. I mean, look, a 12-year-old kid could potentially have kids. They're definitely not somatically mature. They haven't achieved adult size, but they're sexually mature. And similar here with dinosaurs. Now, this sort of data we can incorporate in aspects of ecology and biology that are known as life history strategies. Life history strategies are ways of looking at how evolution has shaped things like the number of babies born, the lifespan, how long does it take to reach maturity, and so forth, and that different types of patterns tend to be widespread among different types of organisms, different strategies to reproducing, with the goal of reproducing at about the rate of replacement. So, for any given pair of adults, on average, you would expect a pair of their offspring to make it all the way to reproductive adulthood, and that's what keeps populations generally level. And there's different strategies towards achieving this. This is summarized by what is fairly, it's a gross stereotype level, but there's all sorts of variations within it, but it's not a bad way to approach, it's not a bad first approximation. And these are what are called R-selected and K-selected. The R is lowercase, the K is uppercase. It actually has to do with an equation of growth. I'm not going to bore you with the equation of growth, but that's what those variables look like in the equation. So R-selected organisms tend to create large numbers of offspring. Consequently, there's less emphasis on the investment in any one individual, whether that's investment as looking over them in terms of your energy, or even just putting your own somatic material into the babies. They're typically going to be smaller, not larger. The survival likelihood of each individual is quite small for R-selected forms, and they typically are organisms that have shorter lifespans. Basically, the life history strategy is the shotgun approach. You put up lots and lots and lots and lots of little babies with the hope that at least one of them is going to grow up to adulthood. So many ray-finned fish, like tuna, reproduce like that. Pigs are, in terms of placental mammals, a good example of that. Pigs have a whole bunch of babies, a whole bunch of piglets at once, and again, many broods of baby over their lifetime. And those are just some examples of it. You can think of others. In contrast, K-selected organisms tend to create fewer offspring. And there's more emphasis on investment in each individual offspring. That might be expressed as more parental care, but it might simply be more of your metabolic energy that's invested in producing them. Consequently, the survival likelihood of any individual is higher, and the lifespans are generally longer. Examples of this would be many types of sharks. They have a lot fewer offspring than ray-finned fish. Or among, say, the hoofed mammals, the approach that horses use or elephants use. Typically only one or two babies at once, not the big clutch of, the big brood of babies that pigs have. Humans, definitely K-selected, by the way. We should point that out. So when we look at the Dinosaurian approach, dinosaurs are definitely R-selected. And that makes them distinct from most of the surviving parts of Dinosaurian, which relative to the Mesozoic dinosaurs are more K-selected. Although, of course, within modern birds, we have some birds which are more R-selected with lots of babies at once and others that just have one or two. So we can do this by a comparison. And don't worry about, you're not going to be tested on the details of this, just the concepts. These data are on the lecture notes. So we can compare two large-bodied animals, terrestrial herbivores. African elephant, the African bush elephant, and Brontosaurus. Brontosaurus, of course, much larger as an adult than an adult Loxodonta, but still they're big animals. That's as adults. As babies, a baby Loxodonta africana is huge. 220 pounds, 100 kilograms. As I said last time, when born, it's already one of the biggest animals on the Serengeti. It's more massive than essentially all the predators on the Serengeti except for lions, adult lions. A baby Brontosaurus could fit inside a soccer ball. At birth, you get just about 1 to 2 baby elephants. And 2 is extremely rare. Almost all elephant births are solitary. Occasionally, there are twins. We don't have good Brontosaurus clutches per se, but based on other sauropods, something like 12 to 20 being born at once seems quite reasonable. We have clutches of eggs in sort of the 24 range for sauropods, but not every egg necessarily is going to hatch. Birth frequency, in the case of placental mammals, as we'll talk about more at the end of today's lecture, gestation period tends to scale with body size. And Loxodonta, the African elephant, has about a 2-year gestation period, at the end of which you get one baby. In the case of Brontosaurus, you could easily have one clutch a year, possibly multiple clutches, we don't know, but easily one clutch of eggs a year. Age at maturity, we'll say it's probably about the same, although it might be a little old, it might be a little earlier in Brontosaurus, at least potentially, and some domestic elephants tend to wait longer. And then lifespan, many decades for the elephant and a little shorter probably for a big sauropod like Brontosaurus, maybe even shorter than that. So let's see how this looks. When the mama Loxodonta and the mama Brontosaurus reach sexual maturity, at the end of the first year, even if she's pregnant, the elephant hasn't had a baby, the Brontosaurus has popped out 12 little sauropodlets. At the end of the second year, the elephant finally gives birth to her baby, the sauropod has another set of a dozen. After 10 years, if the elephant's lucky, it has had produced 5 babies. The Brontosaurus has produced 120. Over the course of their reproductive lifestyle, assuming maturity at 20 and reproducing until they're 50 years old, a really lucky elephant has produced 15 babies. A really lucky Brontosaurus has produced 360. But not counting grandkids, great-grandkids, and etc. If we're looking at rate of replacement, this means there's about a 13% chance of any one baby of the elephant making its way to adulthood and reproducing itself. In the case of the sauropod, less than 1% for any one individual. So, sorry to tell you, Land Before Time, total lie. They also don't sing and dance. Sauropods didn't have, or non-ape dinosaurs didn't have nuclear families with, a couple parents and a couple kids, and Littlefoot's chances of survival were less than 1%. Or Holtz's first law of Mesozoic paleoecology, in the Mesozoic, life was cheap. All right. So now moving over to the new topic for the day, which is dinosaur size. And it ties in, of course, to growth rates. And so, dinosaurs are famously big. Now, as you guys all know, at this point, not all dinosaurs are big. And the smallest dinosaur that we know of is the bee hummingbird. And the smallest Mesozoic dinosaurs would include some of the birds and maybe Scansoriopterigids. But dinosaurs were famously big. In fact, remember, Dinosauria, fearfully great lizards, the name even comes from the fact that they exceeded all known living reptiles at the time. And there are many species of dinosaurs which greatly exceed the large land mammals of today. And there's just 3, Patagotitan, a big titanosaur, Tyrannosaurus, and Triceratops, compared to the 3 of the giant animals of the modern world. Now, the blue whale does remain the largest animal known in Earth history. So the largest animal that has ever lived lives today. The fin whale, the second largest living animal, is comparably big to the very, very largest known dinosaurs in terms of mass. But overall, there were many more types of giant dinosaur than there are giant mammals. And just to map that out, here's Giganotosaurus, Tyrannosaurus rex, Shantungosaurus, the biggest hadrosaur, the biggest ornithopod, Triceratops, one of the biggest ceratopsians, a series of sauropods, a big ankylosaur. And compared to them, there's a human being. There is one of the biggest marine reptiles known. It's an ichthyosaur. A big modern elephant, the biggest extinct elephant, and a giant extinct hornless rhino, one of the largest land mammals. We'll get back to them at the end of this. So how is it that dinosaurs achieved such tremendous size? That's what we're going to look at for the rest of this lecture. This basically reinforces the same thing. Giant extinct dinosaurs, much faster, not only than modern and recent giant land mammals, far bigger than the largest land herbivores among the reptiles today. And although not all dinosaurs are giant, almost every group of dinosaurs produces giants. Here's Shantungosaurus, the largest of the ornithopods. Here's one of the largest of the ceratopsians. A couple different groups sort of max out at around the same size. One of the biggest ankylosaurs. Ankylosaurus is up in about the same range. There's Tyrannosaurus rex, that's the specimen Sue, or a cassivit, and me in front of it for scale from back in 2005. Other theropod groups also achieved comparable size. So here's the giant ornithomimosaur Dinochirus. Here's a highly reconstructed, and now we know wrong, Spinosaurus skeleton. Dinosaurs famously, sauropods in particular, so famous they knock you on the back, so you measure yourself against it, whether it's a humerus or a cervical vertebra or a forelimb of a dinosaur, hind limb. And here's Patagotitan on display at the Field Museum in Chicago, dwarfing the people around it. So you're getting the point. Some dinosaurs were big. In fact, lots of dinosaurs were big. Here's a single metacarpal of Brachiosaurus, and the scientist here has drawn over his hand a metacarpal for scale. So, yeah, they're big, you know that. Diplodocus, it's huge. Saurophagonax, pretty big. Alamosaurus, big, dwarfing Tyrannosaurus there. In fact, in general, as those last two figures show, the biggest sauropods were typically about an order of magnitude larger than the largest theropods. And that pattern held for most of dinosaur history. It's not an unusual pattern. We actually see that happen in a lot of mammalian history, too, where the largest herbivores are about 10 times as big as the largest carnivores. But I was there talking about body sizes, body masses. How can we figure that out? You can't do it the way you might figure the mass of your cat or your dog. There's the simple method. If they're being quiet, you put them on the scale. If they're not being quiet, the way you figure it out is you weigh yourself. You weigh yourself holding the animal, and then you subtract the one from the other. You get the animal's weight. Well, you can't do that. A, these guys would be too big to hold. B, they're not around anymore. So how do we figure it out? One of the best options is if you've got a whole skeleton of one individual, you estimate the volume of the body, you figure out the volume of hollow spaces like the lungs and so forth, and then you multiply, maybe by segmenting the skeleton by the density of the tissue in that part of the body. That's computationally difficult. It requires good skeletons. It requires good skeletons of one individual. You don't want to use multiple individuals typically because they might give you incorrect proportions. And some of that's really unknown stuff. So, secondary method is you do this for the best specimens and then find some sort of linear measurement, like a length of a bone or a circumference of a bone, and scale that to the better known specimens. And then use mass estimations based on these linear measurements, which are easier to get. Of course, what turns out to be even easier, as it happens, is a lot of modern animals tend to scale along the same basic pattern with an appropriate amount of error bar, so that you can derive the equations from modern creatures for which we are more confident of the mass, because we can actually measure those masses. But there are big uncertainties here, and to give you a sense of the scale of the uncertainties. Okay, so this is an example of taking a bunch of measurements. In this case, it's the log of the femur plus the humerus circumference. And the data there are mostly for quadrupeds, and then if we just took the human data, we would find it scaling incorrectly, and that's because we're not using our forelimbs to move. And so, but there's a simple correction you could do, and that plots humans in along the right area. So using this sort of data, trying to estimate the mass of Tyrannosaurus rex, and think about this. Mass is not the property of a taxon. What is the mass of a human? I think once I asked that question, you could see obviously that is not a good question. Is the mass of Jason Momoa the same as the mass of, who's a tiny little actress around these days? Or Ariana Grande. What's that? Oh, there we go, yeah. So, you can get these gigantic ranges within one taxon. So obviously, saying what is the mass of Tyrannosaurus rex? There were big individuals, there were small adult individuals, and of course there were non-adults too, that's something to consider. So these are 5 different individuals, although these two are almost the same size in terms of linear measurements, so they're shown here. And the different estimates done over the course of decades using different techniques, and you can see radically different levels. Masses for Sioux up into, the over 18 tons. That's wrong. That's just plain wrong. Even this 14-ton value, I can't believe that. That's not a believable value to me. I think the ones actually in red are not bad, and I've typically been using these values from that study or that technique throughout the course when it mentioned masses. But you can see a big range. Or here, looking at an individual specimen of Stegosaurus, but basing it on different techniques, you can get a wide variety of ranges. But overall, we get not horrible things, and as long as we're consistent, we're not bad. And then we can ask the question, were dinosaurs actually big? Is it just our perception of them? And yeah, they're big. And here we can see it mathematically shown. Oh, sorry, here. So here are Mesozoic dinosaurs. I believe it's actually Mesozoic non-avian dinosaurs, but even if we added Mesozoic birds in, they would be filling in down here. Oh, notice log mass at the bottom. These are Cenozoic birds. And for comparison, non-dinosaurian modern reptiles. So modern reptiles are exclusive of birds. Modern amphibians, modern fish, modern mammals, pterosaurs, and modern, all Cenozoic, modern plus extinct mammals. And we see that the peak of non-avian dinosaurs was actually quite skewed off to the side, especially compared to even modern placental mammals, or modern and Cenozoic placental mammals. And this is showing the same thing by time slices for the different groups. And in this one, the green, we can see the birds superimposed over their non-avian dinosaur cousins. Or look at it slightly differently. If we looked at, among mammals, if we distinguished between the flat-footed ones, the plantigrade ones, versus the ones that are digitigrade or unguligrade. So remember, digitigrade walking on the balls of their feet, unguligrade walking on their toe tips. The reason for doing that is dinosaurs, after all, remember, are digitigrade animals, so that might be more comparable. We see that, yeah, non-plantigrade mammals, both modern and extinct, do skew larger, but they still skew smaller than the biggest dinosaurs. In fact, the only Mesozoic dinosaurs down in the tiny scale, the same scale of plantigrade mammals, are the flying dinosaurs. So either members of Aviale or of other Humaniraptoran groups that are capable of some form of aerial locomotion. And that's the same data, just scaled as a increasing proportion over time. So yes, we can say the average Mesozoic dinosaur was big compared to the average Cenozoic mammal. Why was this? Well, people have had a lot of less than reasonable suggestions. It's not something that people just started talking about. Like, the gravity was lower then. This is an example of stupidity. Let's just put it right in a stupid. And I know there's someone on the internet who's been following these things and trying to promote this idea. You are wrong. It is not how science is done. Remember the principles of parsimony and consilience. If our observation is there are these giant creatures in the past, the solution shouldn't be, let's get rid of all of physics as we know it. That is not a parsimonious or conciliant approach, particularly because when physics itself is really strongly supported by a lot of evidence. So let's not overturn all of physics. Or the Earth was spinning faster. People have suggested this. The idea is that maybe there's some sort of centripetal effect that's allowing them to get bigger. Or were they clutching on all the time? And what happened? Maybe that's why we don't find as many bones as we want to. Occasionally they let go and it flung off into space. This is stupid. Earth is being pulled at by a larger body. It was in orbit around a larger body, and the gravity was pulling at them. Now, with the Earth spinning faster, that would really only have an effect towards the equator. We should see a gradient of size towards the equatorial forms. And in the second one, either, if the Earth still is rotating, then other creatures would have to either migrate or like be at rest, and then when the larger body came over, they got up and moved around, and then they have to lie down again. Or they were all concentrated on one side of the world, and that's not what we see. Plus, if you have that level of tidal effect, where you can actually allow much larger creatures, that exceeds the mechanical strength of of a planet. For those of you who've taken planetary science, it's Roche's limit. That's where you get rings. You get a moon or other object around a really big object, and it's beginning tidal effects like that, it gets torn apart. These are no-goes. They all lived in the water. This was a popular, well, for the giants at least, this was a popular idea in the 19th and early 20th century, the idea that sauropods were always snorkeling around to buoy them up. Except, of course, the sedimentology doesn't support that. We see they're found in lots of environments, and there were big dinosaurs that are definitely not found in the water. Or a slight finesse of that. The air was so dense, the air was effectively like water, buoying them around. There's no evidence for that. And in fact, all the evidence shows that the air pressure may be a little higher in some parts of the Mesozoic than today, but not dramatically. So we can throw those out. But then we can begin to think, well, maybe the question, what are the benefits for being big, first of all, before we start talking about how they achieved it? Well, one obvious thing is defense against predation. And there does seem to be this co-evolutionary arms race that, predators tend to increase in size to feed on even bigger prey. And so some of the largest theropods, like the Carcharodontosaurs, tend to co-occur with some of the biggest of the Titanosaurs. And the reason it's a good defense is it's a good defense, at least for adults. If you can achieve extremely large body size, you may place yourself out of easy predation, although your babies would still be subject to attack. Also, within species, larger individuals might be more impressive in mating displays or in intraspecific combat, and more generally in terms of capturing more resources. Now, it's especially true for tall animals like sauropods. The bigger you are, the bigger your feeding envelope. And for a theropod, the bigger you are, the larger forms that you can eat are. So you have effectively more resources. So these are selective reasons why you might get bigger, but it doesn't tell us how you would get bigger, per se. Was it limb position? Was it the fact that dinosaurs had a parasagittal stance? Well, that seems like a no-brainer. We do have some giant, dinosaurian-sized Mesozoic reptiles that's certain. There were members of the crocodilian lineage, which were gigantic, and some of the marine reptiles. But in those cases, those really are buoyed up by the water. Those are aquatic animals. And they don't have this parasagittal stance. But among terrestrial animals, the giants are always ones with a parasagittal stance. They are literally in a good position to get larger. Today, mammals. In the past, dinosaurs. However, although it's a necessary condition, it is not sufficient. Marsupials, for instance, never achieved body size, so far as we know, bigger than Diprotodon, which is the size of a rhino. So they're dwarfed by the biggest placental mammals. And on the Archosaur size, there were some big Rauisuchians among the Pseudasuchians, yes, but they're dwarfed by the biggest dinosaurs. And both marsupials and these advanced Pseudasuchians had parasagittal stance. So it's probably a requirement. You probably can't get that big if you don't have a parasagittal stance, but it's not sufficient. Maybe dinosaurs just grew for a really long time. That was the argument back in the 20th century by some people, but we've just talked about, nope, that's not true. They achieved full body size pretty quickly, in a decade or two. Is it that they had an efficient heart and lung system? We will see next week that is definitely true. They had efficient hearts and efficient lungs, but there are other animals that had efficient hearts and lungs that remained quite small. So it is probably necessary, if you were going to achieve giant size, to have efficient circulatory and respiratory systems? Sure. But it may not be sufficient. Now, how about this attribute of the ecosystems? And this is there's a good similarity here between ecosystems with big modern mammals and big ancient dinosaurs, is they're ecosystems with really short food chains. You know, sunlight powers the plants, the big herbivores eat the plants, the big carnivores eat the herbivores. With very few trophic levels, there's not a lot of energy loss. And that's as distinct from the sunlight powering the plants, which feeds some insects, which feeds some predatory insects or spiders, which feed some insectivores, which feed some little larger animals that eat insectivores, which feed the animals that eat those. Think about the food chains that weasels are in, or that small-bodied cats are in, and so forth. That with so many trophic levels, lots of energy gets lost at each step. Again, this is almost certainly a requirement. You probably can't achieve giant body size on land if you're not in one of these type ecosystems. Something else to consider is maybe it's extrinsic. Maybe it's outside the organisms. One thing that we do know is that atmospheres have changed over time. One of the attributes that changes with the atmosphere is oxygen. Now, oxygen is very hard to read directly from the geologic record. Oxygen is so reactive. I mean, heck, there's an entire sort of chemistry called oxidation, named after oxygen, that we can't read it directly. We have to go through various sorts of approximations. But some data shows that during most of the Mesozoic, that's Triassic, Jurassic, Cretaceous, oxygen levels were higher than they are during the Cenozoic over here. So today, a little over 20%. And, here's another estimate. That was the Jurassic and Cretaceous, so the one in blue showing elevated oxygen. To be fair, there are other models that show it was actually less during the Mesozoic. So, and CO2 levels definitely were higher during most of the Mesozoic compared to today. Well, why should that be important? Well, higher CO2 levels in some experimental models with Mesozoic-style plants, plants that we know were around in the Mesozoic, things like certain types of redwoods and horsetails and ginkgos and so forth, shows that the plants have higher productivity. What's productivity? The amount of nutrients they produce per unit time. And so it might be that a given area of Mesozoic forest was producing more units of energy per unit time than today. So, or from a flip point of view, that the modern world might be a bit starved compared to the Mesozoic. A bigger base of the food chain could support larger sized individuals. Now, an alternative is it just supports more individuals. But one thing it could do is support larger individuals. And so, yeah, increased net primary productivity, so the output of the plants, widens the base of the energy pyramid. And larger sized prey could support larger sized predators. Also, the higher oxygen levels just might make it easier to be a big animal. So think about the equation of aerobic respiration. We haven't seen it for a while, but there it is. Food plus oxygen, and then the output is CO2 and CO2, water, and energy. So if there's more glucose available, and maybe there's more oxygen available, it might just be easier to get energy. So it was an easier world to live in, so you can achieve giant size. So it might be this extrinsic stuff going on that is allowing it. However, an important observation made by several scientists is maybe we've been asking the wrong question. The question might not be, well, how did dinosaurs get so big? It might be, why are land mammals so small? Why are land mammals so small? Why do land mammals in their history, get no bigger than about 20 tons, the biggest extinct members of the elephant and rhino level. Dinosaurs and large land mammals have similar attributes. The parasagittal stance, four-chambered hearts, as we will see next week, efficient lungs, ditto. And at least among the larger forms, very short food chains. So here we see a big dinosaur, and it is much bigger than a big rhino. Although, to be fair, that big rhino is still pretty damn big. So why are there so few mammalian land giants? I should point out, again, it's only 2 clades that produce these giants, not the multiple clades we see in Dinosaurian. So, as I mentioned earlier in this lecture, mammal gestation periods are strongly correlated with body size. So horses, about 11 months, rhinos, about 16 months, elephants, 22 months. Following this trend, the largest extinct elephants and the largest extinct rhinos, maybe about a 3-year gestation period, and they get 1 baby after that. That makes living at the rate of replacement difficult. Also, because evolution works by the sorting of variation in a population, you don't have a lot of variation around. So big land mammals may be putting themselves evolutionarily in a bad position where it is very hard to adapt to changes. In contrast, even titanosaurs the size of a herd of elephants are putting out clutches of 24 a year or so. So they have a much bigger standing crop to sort amongst, and a much easier way of having replacements. And here we could see litter size or clutch size of crocodilians and various dinosaurs against body size, and we see mammals, they peter out down to just 1 at about, around over a ton. Now, another thing that people have observed, and we're almost at the end of this one, is that in mammals, the thickness of the articular cartilage, the cartilage that exists at the ends of the joints, scales with negative allometry. The bigger the animal, the bigger the mammal, the less cushion they have at the joints. In contrast, among living archosaurs, and so far as we can tell from their osteological correlates, in ancient archosaurs, articular cartilage grows at isometry, the same fraction. And so dinosaurs seem to have cushier joints, regardless of how big they got. So it might be that Cenozoic mammals live in a relatively starved world and are trapped through allometry with regard to the form of reproduction and a form of joint ability that makes them less viable at big body size. Whereas dinosaurs didn't have that and could easily achieve that size so long as the environment would support them. Next week, we'll see how some of the things I touched on those last couple lectures, what they might apply for the basic question of the physiology of dinosaurs, which actually, we start next week and it takes us all the way up through Thanksgiving. Take care and have a good weekend.